Given an integer array nums and an integer k, choose exactly k non-empty subarrays. They may overlap and you may repeat the same range. Each subarray scores max minus min inside that range. Goal: maximize the sum of all k scores. First pick indices 0 through 1. Max is 3, min is 1, so the value is 2. Second pick indices 0 through 2. Max is still 3 and min is still 1, value 2 again. 2 plus 2 gives output 4. Example 2. The full array has max 5 and min 1, so each pick scores 4. Choosing that range 3 times yields 4 times 3, output 12. At first glance, this problem looks incredibly daunting. We are tasked with choosing exactly k subarrays to maximize their total score, where each subarray's value is its maximum element minus its minimum element. Your brain instantly starts spinning up complex sliding windows or heavy dynamic programming grids to track how to partition the numbers. But wait. Stop overthinking and look closer at the constraints. The problem explicitly states that subarrays are allowed to overlap, and more importantly, the exact same subarray can be chosen more than once. This completely breaks the puzzle wide open. If we want to maximize our score, we need to find the absolute highest value any single subarray could possibly generate. The largest difference achievable in the entire array will always be the global maximum element minus the global minimum element. We locate those two numbers and isolate the subarray that encapsulates them both. Since we are legally allowed to reuse the exact same subarray as many times as we want, we don't need to search for k different combinations. We can simply take our ultimate, high-scoring maximum subarray and choose it over and over again, exactly k times. 4 times k gives 12. The answer is global max minus global min, multiplied by k. We initialize our code panel on the left, establishing 2 baseline tracker registers on our right track. We set our maximum tracking value to -infinity and our minimum tracking value to +infinity, preparing to find the extreme boundaries of our array. We launch a single, linear iteration pass across the entire array. As our character pointer steps over each element, it continuously updates our 2 registers. By the time the loop completes its final stride, we have isolated the absolute maximum element, 5, and the absolute minimum element, 1. With our global bounds locked in, we subtract the minimum from the maximum to find our optimal single subarray value, 4. To ensure safety against memory overflow, we explicitly cast this value to a 64-bit long integer. Finally, we scale it by our factor k, returning our absolute maximum possible sum, 12. Let n be the length of nums. Time is order n. One linear scan updates the running minimum and maximum in constant time per element. Space is order 1, only a few scalar variables for the extremes and the final product. Pseudocode for max total value. Initialize min and max to infinities, scan the array once updating both extremes, subtract to get the best single subarray value, then multiply by k and return.